of our series into contest math for science competitions. Now, here we'll be going over some high school mathematics tricks, which is essentially taking the skills you gained in high school mathematics or further mathematics to the next level in a capacity that they can benefit you when you're on a time crunch, in a race against time in these science competitions, and you need to do any kind of quantitative analysis very fast. So first off, we'll be starting with integration methods, which I'll be covering. Now, any basic calculus course would introduce you to at least some of the following integration techniques. Integration by parts, which is for when there's a product of two functions and you're trying to integrate that. U substitution, the traditional way, where a function can be split into a subfunction and its derivative, also known as the parent-child relationship, where it's a simple substitution to convert x and dx into some functions of u. Then there is U substitution in reverse, which is for cases when it's not so straightforward, i.e. you're trying to bring the function to look a certain way. For example, if I was trying to integrate the square root of 1 minus x squared, then there's no visible x or dx or a parent-child relationship per se. So I would substitute x is equal to sine u, which would allow me to simplify the entire thing as cos square u du, and many of you must have done this as an example. If not, don't worry, some of these examples are linked in the transcript. But yeah, u substitution in reverse essentially converts x into a function of u, whereas the traditional version takes a function of x which is present in your integral and converts that into u directly. The u is a simplification, and in the reverse process, it's a slightly more complex yet manageable integral. Then the final two techniques are partial fraction decomposition, which is basically for cases when you have a function such as quadratic to integrate, but it's in the denominator. So it's a reciprocal quadratic which can be factored into 2, or even if it's a reciprocal cubic which can be factored, or quartic or so on. And this is the most common technique for integrating reciprocal functions, because once you split them up into partial fractions, each one is simply a logarithm integration, because 1 by x integral is ln x plus c, and the same is true for 1 over x minus 1 or any other factors that you may expect. Finally, you have Maclaurin series, which is for non-elementary integrals. For example, the integral of e raised to x squared, which doesn't have any elementary way of like any recognizable elementary way to integrate it. Of course, some of you may be knowing about the error function fx, but in reality, Maclaurin series provides the most approximate expansion, because even though it's an infinite series, by integrating e raised to x squared Maclaurin series as a power, using the power rule of integration, even within 5 to 6 terms, you can get a very accurate answer. And sometimes this is necessary, even implied in questions, especially of physics and mechanics, which require some sort of approximation for a complex process. Quickly, I will also touch upon differential equations, which we saw in the previous episode, episode 3. There are three main techniques: variable separable, in which case the y and x can be put on different sides; integrating factor, where the where the differential equation is linear in y, but it's a separate term from the x component and the dy by dx component. Then finally, homogeneous is can be for any degree of x and y, provided that the sum of the degrees in the numerator and denominator is essentially equal, which is to say, if you can express dy by dx as a function of f of x and y, then you get the same result if you substitute tx and ty into that equation. Hence the name homogeneous. It's homogeneous in the x's and y's. So more information and resources into these particular techniques is given in the transcript, as not all of you calculus students must be fully familiar with all of these. Now I'll be handing it over to him to talk about polynomials and roots and factorization.
Now, polynomials, it is basically a mathematical expression involving a sum of powers. Now, each power has its own coefficient, and the highest power is basically the degree n. Now a polynomial with highest power n will only have a maximum of n number of roots. Now a roots is basically when the function is equal to 0. So the values of x for which the function is equal to 0, those are the roots. Now when n is even, both sides of the graph of the polynomial will curve in the same direction. For example, a quadratic. Now a quadratic, if it starts from up, it will go like this and then return upwards as it tends to either infinity or minus infinity. However, for odd functions, they curve in opposite directions. Let's take a line or even a cubic equation. They start from one end and then go to the opposite end. Now, in an even polynomial, if the leading coefficient is negative, then the function heads to minus infinity as x goes to infinity or negative infinity. Now the sum of the roots is minus b by a. Now b is the coefficient of the second largest power term and a is the leading term's coefficient. Now the product of the roots is basically the constant term divided by the leading coefficient. However, there is a sign associated with it. The sign is negative when the degree is odd. For example, for either a cubic or a quintic. Now coming back to factorization. Now factorization relates to polynomials. Now factorization is basically breaking down a polynomial into multiple linear factors. For example, splitting a quadratic into two factors. Now this is very easy for quadratic. However, for like larger functions such as cubic or quartic, it becomes a very lengthy process. However, techniques such as long division or synthetic division definitely ease this process. Now a property of factors is if x minus a is a factor of a polynomial, then f of a will equal to 0, which says that a is an x-intercept.
Okay. Now we move on to the types of proof, which is also going to be covered by him because of his experience in various types of proofs. But I just want to touch upon why this is important in physics and chemistry computations in particular. Often you'll see show that questions, especially if it's an exam such as advanced placement, which has a free response section. And while the proving skills you need aren't as rigorous for types of proofs in physics and chemistry, usually you'll be okay if you just know simple deductive or just how to solve a system of equations. However, it's very helpful in when you learn these different types of proofs, it's very helpful to see the relationships between different types of equations and numbers and quantities, and it's just a very good practice that inculcates. And of course, if you're in a pure mathematics competition, very common example is the American math competition, AMC, or CEMC's Euclid or high pressure or something like that. Then all of these types of proofs will be very beneficial because often when one type fails, the other one is always there to take over. He'll be covering simple deductive, then there'll be counter example, and finally proof by induction, which will be covered in most high school math, 11th and 12th grade level math courses, or at least in first to second year of university typically. Over to you.
Thanks so much, Anish. Now, simple deductive reasoning is mostly show that or else is equal to RHS. When solving, we can only manipulate one side of the equation, and we have to show that this one side of the equation is equal to the other side. Now, this tends to be very common in science-based papers. However, in mathematics, you may get a combination of multiple types of proofs. Now, coming to the second one, proof by counterexample. Now in proof by counterexample, it is where you prove a statement false by providing a counterexample. Now, you give an example of basically a scenario where your condition is proved false. Hence, that is counterexample. Now, coming to the third proof, proof by mathematical induction. Now, mathematical induction is very unique, and what happens here is you induce the proof. Now, there are three steps of mathematical induction. In the first, which is called the base step, you basically assume the lowest possible value and you prove whether that holds true. In the second step, you assume P of k holds true or for any variable k. After that, you basically replace your variable with k plus 1 and you try to prove that k plus 1 holds true. If you are successful in doing so, what you have basically done is induce the proof. Since we have assumed a minimum value, if the value is 1 greater, then that is also true. And since that's true, we can say that the next term is also true. Hence, we create a chain, and hence we are inducing the proof.
That is true for every single possible value, typically integers.
Yep.